Distinguished guests, ladies and gentlemen, welcome back to the second day of Virtual Nuclear Power Plants Expo and Summit. Today, we will complete our summit with keynote speeches and sessions. First of all, for today, I would like to welcome Mr. Orkun Hasekioğlu, Vice President of National Energy, Nuclear and Mining Research Institute of Turkey, Department of Energy, to make his keynote speech about towards generation for energy reactors in Turkey.
Thank you for the introduction. The title of my speech, as was introduced, is Our Journey Towards the Generation for Advanced Energy Reactors. I'm currently serving at TENMAK, Energy, Nuclear and Mining Research Institutes of Turkey, affiliated with the Ministry of Energy in Turkey. I must say initially in the beginning that this is a joint governmental project that covers all the relevant facilities, research facilities in Turkey, including TÜBİTAK, the institute I was serving as vice president previously, and our universities as well as industry. Here's the outline of my presentation. I will start introducing Generation 4 Forum, the general concepts on Generation 4 reactors, in particular molten salt reactors, and the justification as to why we have picked molten salt reactors as our national project. And then I'll continue with Turkey's bid to join the Generation 4 Forum, our current status in that regard. I will continue with our capabilities and contribution to potential contributions to Generation 4 reactor concepts, and finally Turkish molten salt reactor roadmap. Our journey towards advanced reactors in Turkey goes back to 2016. I just recalled my opening remarks in the 2017 NPP summit in Istanbul. In that introductory speech, we had mentioned, I was serving as vice president at TÜBİTAK at the time. The thorium molten salt reactor is a fourth generation reactor technology that offers low cost electricity and heat, high level of safety, low level of nuclear waste, along with ease of operation. The thorium molten salt reactor, which relies on Turkey's national thorium resources, can be built using national resources and capabilities. Briefly, Generation 4 advanced reactors we expect that it will revolutionize energy production. All the other reactor concepts, starting from Generation 1, Generation 2, 3, and 3 plus, are referred to as evolutionary designs. Conceptually and technologically, they are all similar. Generation 4 reactors, on the other hand, they are referred to as revolutionary designs. The conceptual approach to nuclear energy production is entirely different in these approaches. And it's expected that by the year 2030, the Generation 4 energy reactors, nuclear energy reactors, will be in widespread use worldwide. And the main motivation behind developing or designing Generation 4 reactors is more safety, sustainable energy production, economy, low cost of energy production, and proliferation resistance as compared to the previous Generation 3 and Generation 3 plus reactors. As I mentioned, the major objectives of the reason why we are introducing these reactor concepts worldwide is sustainable, low cost, safe, and proliferation resistant nuclear energy production. This is the governance structure of the Generation 4 Forum. This is a platform where all the countries that has potential to generate technology in nuclear energy is get together and produce and collaborate in such technological endeavors. And the policy group is headed by the director of JAEA, is the main governing body of the Generation 4 Forum. The current GIF membership, as I said, it's a technology partnership program, is participated by all the nuclear energy capable countries, including United States, Canada, China, Japan, Russia, and most of the European countries are covered under the Euratom program. The Generation 4 Forum that was established back in the year 2000 put together a group of experts, nuclear reactor design experts, and out of over 130 design alternatives, this group of experts selected 6 reactor designs that we refer to as the advanced reactor designs. And under this forum, as we mentioned, there are many countries participating in this forum. There are subgroups of research collaboration pertaining to all of the 6 major nuclear reactor design concepts. And one of them is MSR, molten salt reactors, and there are 5 other reactor designs. And countries, various countries, signatory of this forum, they collaborate on these advanced reactor design technologies. And as I mentioned, the molten salt reactor is one of the leading advanced reactor concepts among these 6 designs. In this particular design, the fuel as well as the coolant is in the form of molten salt of thorium, uranium, and lithium, and in certain cases beryllium fluoride or chloride salts. So the energy, the heat energy produced as a result of the fission of the fissile material in the salt is transferred through a heat exchanger through a secondary energy conversion to electricity. And in many instances, it may be desirable to actually utilize the heat directly. One might ask why we have selected molten salt reactors among the 6 advanced reactor designs nationally, or why we and what's the motivation behind this. The history of the molten salt reactors actually goes back to 1950s to the Oak Ridge National Lab. At the time, the Oak Ridge National Lab in the 1940s and 50s was named as the Clinton Laboratories, and the Clinton Laboratories was mandated to construct the world's first operational nuclear reactor. And its second objective was to develop chemical processing facilities to separate plutonium from the irradiated fuel. And this is back in 1960s, I think. This is how the Oak Ridge National Lab in the United States looked like. The concept of molten salt reactors started as a reactor for the propulsion of a jet engine, and it was referred to at the time in 1958 as the aircraft reactor experiment. But then it was pretty soon recognized that it's not convenient to use nuclear reactors on plane because of the neutron radiation isolation issues. But the research continued under the name molten salt reactor experiment. And during the time between 1964 and 1969, a 7.4 megawatt thermal reactor operated in the Oak Ridge National Lab. So the takeaway lesson from this is MSR is actually conceptually, at least, not commercially, but it's a conceptually proven technology. This was one of our main motivations. But this is the current picture from the Oak Ridge National Lab. It's now actually, as you all know, it's a huge lab employing 3,000 researchers with an annual budget of over 1,005 billion USD. It also actually houses the summit, you know, the supercomputer, the world's most powerful supercomputer summit at the same time. We actually had a visit to the Oak Ridge National Lab back in 2017 and get to know some of the, actually many of them, of course, passed away, but some of the participants of the aircraft reactor experiment and MSRE experiment. These experiments were stopped by the administration at the time, and the current light water reactor technology was preferred, and Oak Ridge National Lab at the time continued working on the light water reactor technology as well as the other parts of the world. But the director of the lab at the time, Alvin Weinberg, and physicist, the famous physicist Eugene Wigner, were the masterminds, you know, of this project at the time. And the reason of our visit was to offer a joint collaborative work on the Generation 4 reactors together with the Oak Ridge National Lab. But the suggestion we got at this meeting was to join GIF and the Generation 4 Forum and pursue our joint efforts through this forum. More recently, back in maybe 2017 or 2016, the molten salt reactor research at Oak Ridge National Lab was revived. You know, there is a revived interest in pursuing and developing molten salt reactors. The facility you see in the back is a molten salt flow loop, a test facility that we had visited at the time. So as a result of all these, the early history and the expertise that's developed through the Generation 4 Forum and currently especially the introduction of this technology through the commercial companies, TerraPower and many others right now, this early success ignited a current and very strong commercial interest recently during the past few years. These are some of the major characteristics of molten salt reactors as compared to other conventional reactors. For the most part, these characteristics eliminate the safety concerns that are attributed to the current light water reactor technologies. It produces less spent fuel. Use of light water reactor waste as fuel is possible. It's a high energy density, enables production of a wide range of nuclear reactors, you know, from megawatt, hundreds of megawatts to a gigawatt range. As you know, the major concern, one of the main reasons why Fukushima and Chernobyl disasters happened was the core melting problem. The core melting is not possible in this case because the fuel is already in molten form. The load following property, the energy produced follows the demand in the grid. That's an important because that eliminates the need to store the produced energy. In addition, the passive reactivity control inherent to the design of the reactor and low operating pressure, 1 atmosphere actually, is compared to the few hundred bars in conventional reactors makes this kind of a design very much safe, as compared to the current reactors. In addition, one of the other motivations that made us pursue molten salt reactors was that the generation 4 commercialization, it's the worldwide, this commercialization efforts are gaining momentum. In addition, the GIF annual reports, progress reports, in many cases identifies the molten salt reactors as one of the mature designs among the 5 other or 6 total designs. Additionally, internationally, many research institutes, including WABA, Institute of India, and Chinese Academy of Sciences, SINAP, adopted this technology or variants of this technology, I must say, as within their national strategies. China now is investing in commercial construction of an MSR reactor in the gigawatt range. And additionally, over a dozen private companies worldwide in the US, Canada, and Europe, they have adopted this variants of molten salt reactor technology, MSR like technologies, I would like to call, including TerraPower. All these indicate, the commercialization potential. It's not only in research level, but commercially, that MSR is a viable technology. So all these brought together motivated us to attempt to adapt this technology as a national, within our national roadmap. Back in 2017, at TÜBİTAK, I was serving as the president of Marmara Research Center at the time. We had an international workshop together with CNRS. And as a result of this workshop, there was an advice to collaborate on fast breeding molten salt reactors. Because molten salt reactors also, they have, as I said, different variants. It could utilize slow neutron spectrum or fast. It could be breeding or non-breeding. So we discussed in this symposium, in this workshop, all these variants in detail. And this was in particular one of the design concepts that we discussed in this meeting. So, a few words about our bid to join the Generation 4 Forum. As I said, the story of our journey to joining Generation 4 Forum goes back to 2016. The National Council of Science and Technology, in the meeting in 2016, that's headed by the Prime Minister at the time, issued a decree to plan for advanced nuclear energy technologies. And then in TÜBİTAK, where I was serving as vice president at the time, the Science Council of, in other words, the governing board of TÜBİTAK at the time, made a decision in its meeting in November 2017 to participate in the GIF platform. And as a consequence of this, our official application of GIF membership by the Ministry of Science and Technology was submitted to the policy group governing board of the GIF platform. And there are many other supporting policy documents, decrees, and strategy plans regarding this. I'm not going to go all over them, but there is mention of participating in these technologies. And then, as a consequence of this, our case was presented to the GIF policy group in Paris, in a meeting in Paris in 2018. In this meeting, we presented to the policy group how Turkey can contribute and the relevant capabilities of Turkey in case if Turkey joins to the GIF platform. As a result, the policy group issued a report back in August 2019 saying that we have as GIF experts, we have observed that Turkey has the capability and potentiality to provide mutual benefit, added value for GIF organizations, members and participants. And then they accepted our application on one condition, that this has to be a multi-year, there has to be a multi-year research plan that's adopted by the government of Turkey. Briefly, I would like to talk about some of the ways that Turkey, infrastructure of Turkey, will contribute and is contributing to the MSR research. The Turkish technology infrastructure, as we have observed and we have demonstrated to the internationally to the GIF policy group, our infrastructure embodies many of the capabilities that is essential to design, build, and operate an MSR reactor. And I will indicate, some of these capabilities. In Denmark, TR2, it's currently dysfunctional, but we are in the process of replacing this research reactor. This research reactor is going to be an important tool in doing the irradiation tests. In the past, this facility was used to produce medical radioisotopes, but it's the neutron flux of this facility is sufficient to conduct irradiation tests on the salt, molten salt, as well as the structural components. Similarly, there's another research reactor in Istanbul Technical University, Triga Mark II. It's also it can be used for salt and material irradiation tests. At the Marmara Research Center of TÜBİTAK, we have a facility to build for different purposes. It's a dual-use technology, silicon carbide composite parts for the aviation industry. And in many applications, this silicon carbide material is suitable for building reactor parts, to manufacture and reactor parts. So this facility is suitable in that respect. Additionally, TÜBİTAK, again, the Marmara Research Center, the critical metallic materials laboratory is a lab where we produce nickel-based superalloys and actually manufacture components that are used in gas turbine jet engines out of these components. And this also material technology, haste alloy and other alloys that are based on nickels, they are crucial, in the development of different reactor components and parts. So we have all the stages from CAD design to casting, coating, and heat treatment and characterization available to produce such parts using superalloys. Our isotope enrichment program, we are not interested in this particular project for boron isotope enrichment, but the same ion diffusion exchange facility can be used to separate lithium-6 and lithium-7, for instance. Again, in TÜBİTAK Marmara Research Center, we have facilities where we handle compounds, of molten salts of sodium, calcium, and lithium chloride flow loops. And so the experience in this production and handling of molten salts is crucial, again, in this technology. Similarly, the Energy Institute of the Marmara Research Center of TÜBİTAK, the balance of plant, the secondary cycle where we generate electricity out of the heat produced is an important contribution. A site assessment study in Sinop nuclear reactor site, nuclear power plant site was done by, again, TÜBİTAK Marmara Research Center. We have an institute on rare earth elements and thorium. And thorium is one of the key. Thorium itself is not a fissile material, but it's a fertile material that could be converted internally to a fissile fuel. So this institute is dealing with that technology. Our membership with CERN, design and testing of sensors, readout circuits and ICs, operating at extreme high radiation conditions is relevant. Our joint work with CERN is relevant in this regard. And this is an outline of potential GIF research participation that I have discussed. I'm not going to go over this outline, but this just basically summarizes what I have told you so far. Currently, this is where we are. Our national roadmap for advanced reactors that we have been studying during the past few months in the National Molten Salt Reactor Roadmap Study Group within the Turkish Presidency Science, Technology and Innovation Policies Board has been completed. It's quite a lengthy report. And this report outlines a roadmap for advanced reactors, a 10-year plan actually for building an advanced molten salt reactor. So once it is approved and declared as our national plan, we will, through this plan, we will continue, of course, our national work internally, but also our application process to the GIF platform. And this is a 10-year plan. Our 10-year plan includes two reactor concepts: one, a 30 megawatt thermal, a small reactor, another one, 300 megawatt thermal energy nuclear reactor. And this is my email. Thank you for listening to me. I think I have maybe a couple of minutes more. As I said, and this is my email, you are free to contact me directly at this email in case you would like to collaborate with us in these programs. Industry, as well as I mentioned, our academia, nationally as well as internationally, are welcome. I can take questions if there are any. Okay, so I conclude my presentation.
Thank you very much, Mr. Hasekioğlu, for your speech. Ladies and gentlemen, we will start the next session about nuclear projects in multicultural environments in 5 minutes.